What causes overfitting in AI pattern recognition? Imagine teaching a student to recognize animals. If they memorize every single picture they see, they might struggle to identify animals in new photos. That's similar to what happens with overfitting in artificial intelligence pattern recognition. When a machine learning model learns the training data too well, it picks up on details that aren't really part of the pattern. These details can be random noise or small quirks unique to that data set. As a result, the model performs perfectly on the data it was trained on but struggles with new and seen data. In pattern recognition, models learn by adjusting internal settings called parameters. These parameters help the model decide what features are important. If the model has too many parameters or is too complex, it can start memorizing specific examples instead of learning general rules. For example, an image recognition system might memorize textures from the training images rather than understanding what makes a texture generally. When it sees a new image, it might fail because it's expecting the exact textures it memorized. One big cause of overfitting is having too little training data. When the data set is small, the model can easily latch onto quirks that don't reflect the true pattern. Another cause is using a very complex model with many layers or parameters. These models can fit the training data very closely but often end up fitting noise instead of the real signal. Poor data quality also plays a role. Noisy or inconsistent data can mislead the model during training, making it learn incorrect patterns. If a model is trained for too many rounds or iterations without checks, overfitting can happen. This is because the model keeps adjusting itself to fit every detail, including the noise. Detecting overfitting involves comparing how well the model performs on training data versus new data. If it does very well on training data but poorly on new data, overfitting is likely. Cross-validation is a common method where the data is split into parts for training and testing. If the model's performance drops significantly on the test data, it's a sign of overfitting. To prevent overfitting, data diversity is key. Using more varied and larger data sets helps the model learn general patterns. Simplifying the model by reducing layers or parameters can also help. Techniques like dropout, where some parts of the model are ignored randomly during training, can prevent the model from relying too much on specific features. Regularization methods, such as L1 or L2 regularization, add penalties for overly complex models. Early stopping, which halts training when the model stops improving on validation data, is another effective way. In real-world applications like ChatGPT, DALL-E, and Midjourney, overfitting can cause outputs to be too specific or odd, not matching new requests well. For productivity tools, overfitting might make features work great in tests but fail in actual use. Managing overfitting is not just about technical accuracy, it also ties into fairness and trust. Overfit models can make biased or unreliable decisions, which can harm user confidence. Understanding how to spot and prevent overfitting is a vital part of building reliable AI systems. Balancing the complexity of the model, the quality and size of data, and proper validation helps create systems that work well in many different situations. This balance is essential for developing AI that can recognize patterns accurately and fairly across a wide range of tasks.